In this last part of the exercise 5, we have to fit an analytical IDF equation to the points that we have created in the empirical IDF. Just to quick summary of what we have done so far, if we go to the complete notebook, on top we have the steps that we have to proceed. So there are five steps, and we have already done 4 of them. First, we imported the hourly precipitation series. Then we created a series of annual maximum precipitation for several storm durations. Later on, we fitted GeV distributions to each of these storm durations. And lastly, we calculated the points in empirical IDF, which are these ones here. Now we have to fit an analytical CDF to these points in that plot to create a plot similar to this one here. So we have continuous curves for each of the return periods. If we go here down to the analytical IDF curves, here I show you a few equations. There are several forms that the analytical IDF curve can get. So different equations that several researchers have developed, and we have to create a function that calculates each of these forms of the analytical IDF curve. Revert. Okay. So we get into our solution, and so we go. The last part of the exercise is analytical solution. Sorry, analytical IDF curves. And we have to create a function for each of these, okay, like this one here. I'm just gonna do it for one of the IDF types, and the rest of them we're just gonna drag and drop the function from here. So remember, to create a function, we have to use the def and then give the name of to the function. So IDF type 1, and then in parentheses we set the attributes of the function. So it's going to be a x for the data, b, c, and d. Okay. With 3 query marks, we give the help to the function. So estimate precipitation intensity given a return period and a duration. And the equation is intensity equals A multiplied by R plus P divided by D plus C. Okay, and we have to specify what are the inputs. So anyone who uses this function knows what x, a, b, c, and d are. So x is a list of values which must have this shape, two values. So our values of return period and duration. A, B, C, and D are floating point numbers and are parameters of the IDF curve. And the output which is E, is a floating point number and is the precipitation intensity in millimeters per hour. Okay. Once we are done with the help, we proceed to introduce the code inside the function. So our function has only one line, which is just replicating this equation here. But now instead of R, we're gonna call it x0. So the first value in x has to be the return period, and b is the second value in x. Okay, and important, the last thing in a function is the return. So this is done internally, and we're only gonna return whatever is in after this return statement, and we're gonna return I. With this we have a function which is type I, okay, and you see here is the help that we just created. The better the help, the better explained, you will be able to work with this function later on. So not to spend a lot of time, I'm just gonna copy the rest of the functions here. Remember to delete, sorry, I just did that pretty quickly. I have all the function in one single cell, so if I want to clip a cell or cut it, we just select where we want to cut the cell and then Control Shift hyphen, and we split the cell in two, and then we can just drag and drop. Good. And now we have the function that we created for type 1 IDF, and we just imported 2, 3, and 4. Okay, the 4 types of IDF curves. So now we have all of them. So if we just go here and then Shift Tab, we have the help for IDF type 4, which is this one here. Good. Okay. So let's fit the analytical IDF. Good. To fit a function, we're gonna use SciPy optimize, and from that SciPy optimize package, we're gonna import curve fit, which we have already used in previous exercise. In curve fit, we need to input 3 attributes. Okay, so one is the function to be imported. For instance, it could be the IDF type 4, and then we have to give X data and Y data. X data is going to be this series here, and Y data in our case is going to be the value of intensity for each of these points. So Y data is going to be the value of intensity for each of these points, okay? And the X data is going to be the coordinates of each of these points in terms of return period and duration. So we have to create this X and Y. Let's create the dependent variable in the IDF curve, which is intensity. So I repeat, we have to create a Y data, which is a vector with all the intensity values for these 18 points. How are we gonna do that? So let's create an empty NumPy array with shape 0. So Y is empty, and now we're gonna just put a vector with all the values of intensity. How are we gonna do that? Remember that we have a table with our results. So we need to put all these 18 values in one single row. So we're gonna take these 3 values for duration 1, then put followed by the 3 values of duration 2, followed by the 3 values of duration 4, etc., etc. So we need a loop across duration. So for D in duration, okay, we are use a function called concatenate. Concatenate is just collapsing several vectors. So let's just do it, for instance, for duration 1, okay? And we're gonna concatenate the original I, which in the first step is empty, with the values of this table for column 1. Okay, so now you see we had originally an empty vector, and we have concatenate these 3 values, so now we have a vector with 3 values, 13, 20, and 24. If we put here 1 and 2, we get the same 3 vectors for 3 values for duration 1, 13, 20, 24, followed by the values for duration 2, which are, oh, sorry, that was a mistake here. Followed by the values for duration 2, which are 9, 14, and 16, 9, 14, and 16. Okay, so if we do that is for every duration, we get a I vector with 18 values, which are these 18 values. And we can see that the last value is exactly this one, and the first value is exactly this one. Okay, so we created the dependent variable. Now let's go to the toughest part, which is the independent variable in the IDF curve, which is per values of return period and duration. Okay, so we need to create this had shape 18, so now we have to create a new array with 2 rows and 18 values, which are corresponding, each row corresponds to the duration or the return period. So remember, we have R and D, which are return periods and duration. So 3 return periods, 6 duration. If we use this function mesh grid R and D, we get 2 vectors. Let's call it R and DT. Okay. And then let's see the shape. So we created, these were shape 3 and shape 6. So now I have 2 vectors of both shape 6 and 3. If we see one of them, so we see that for each column represents a return period and each row represents a duration. And we have the coordinates of those 18 points. So let's say the first value here in the I. So this first value here corresponds to coordinates of 2 and 1 in terms of return period and duration. Okay. And the last value here corresponds to the coordinates 30 and 24 in terms of return period and duration. We need to flatten these vectors because they have dimension 2 and we have to convert them to dimension 1. Okay, to do that we just do this. There's flatten dd flatten. And now we can see that RR and DD are 2 vectors, are the same values but just organized in one single vector each. And now we're gonna stack them together in one single array, which are, we're gonna call it RD, and we're gonna use vertical stack with RR and DD. And you'll see that RD has a shape of 2 rows, 18 columns. And if we plot it, okay, we have this value. So the first row represents the return period and the second row represents the duration. And we have to check that this is the intensity corresponding to a return period of 2 and a storm duration of 1. If we plot the table E, we see that return period of 2 and intensity storm duration of 1 has a value of 13.15, which is this one here. And we can check, for instance, that the fourth value, which is 9.49, this one here, should get a return period of 2 and a storm duration of 2. So the fourth value would be 1, 2, 3, 4, return period of 2 and duration of 2, etc., etc. If we go, for instance, to the last value, which is 338 here, corresponds to 30-year return period and 24 hours. So the last value here is 30-year return period and 24 hours. Okay. You will have to think a little bit about this. I know it's not so easy in the beginning, but then you will just understand that these are the coordinates in terms of the return period and duration for each of these values. Once we've done all this, we can fit the curve. So first we set the type of IDF. So let's call it curve. And we're gonna work with the IDF type 4. You can check any of them, type 1, 2, 3, or 4. I'm just gonna stick to this one. And then remember, we're gonna use the function curve fit in SciPy optimize. The first attribute is the type of curve or function. So we just introduce this curve that we just created. And then we have to provide the x and y, which are RD, and the y is I. and this gives us two vectors. One is the parameters, and the second one is the covariant matrix. It's a type of performance in the fitting. So we only are interested in the first vector, which are the optimized parameters. So remember that type 4 has 4 parameters, A, B, C, and D. These are the 4 values that we got here, A, B, C, and D. We can just save it as parameters of the IDF curve. And if we want to plot them, this will be parameters. Okay, good. Let's save these optimized parameters. Save optimized parameters, because this is one of the results of our exercise. So we're going to create a data frame called IDF-A for analytic data frame, and the data is going to be our parameters of the IDF, and the column, the index is going to be the name of the parameter. So A, B, C, and D. If we plot it, we have a series. I liked it better to transpose the matrix, so to do that we just do here transpose, and we just change the shape of the table. And now we can directly export this to a CSV file. We have to introduce where we want to save this table. So output, exercise 5, parameters, analytical IDF, CSV, and let's set the format of the floating point numbers, float format. With this code here, we're setting 5 decimal points. Okay, so now in the output folder, so this was the main folder. In output, we have exercise 5 analytical parameters, analytical IDF, and we have the values of A, B, C, and D. Okay, we can improve this a little bit if we just include index equals false. So now we don't have A0 here. So A has this value, B has this value, C and D. Okay, good. And last thing in the whole exercise, we're gonna visualize the fit. Okay. So as usual, we set size to the figure. This is going to be 10 by 4, and then let's set some configuration parameters. So we're going to create a limit to the x-axis 0, and then let's put 25 hours maximum duration. Then create the label for the x-axis, duration in hours, a label to the y-axis, which is intensity in millimeters per hour, and then we can just copy this from the plot here. Good. And then let's create a linearly spaced array of durations. So from 1 to 25, let's create 100 values of duration. This means that now it's not single values of 1 hour, 2 hours, 3 hours, but different, okay, floating point numbers. And now we're gonna create for each return period. We have already used this enumerate in the previous part of this exercise. And now let's create a return period with this a return period vector with the same shape as this one, Okay, to do that we are going to create ones like this creates a vector of all ones with the same shape as this one, and then we multiply by the return period. So we created a vector with the same shape as the underscore with the value of the return period for this iteration. And then we create the intensity. So we use the curve. Remember, curve is the IDF type 4. And we have to input our vectors of return period and duration and the parameters, which are in this object. Remember the asterisk, in this case, there's no space. It means that we should introduce here 4 parameters, A, B, C, and D, and we are introducing them all together in this object par IDF. Okay. And now we can plot for the duration, the values of the IDF empirical. Let's copy this from top, which is going to be faster. So I'm just copying this values here. Okay. So this is to plot the dots of the empirical IDF, and now we're going to plot the analytical IDF. So for duration, E, and we give a color according to the return period. The last thing is to create the legend, so fig legend, and we give a location which is 8, means on the at the bottom, and number of columns which is 3, the number of return periods. Okay, so we created this plot here. Okay, so each line represents a return period, and then we have duration on the x-axis and intensity on the y-axis. If we want to save this figure, PLT save figure, we set the location where we want to save it. So exercise 5, analytical IDS, PNG, and then the resolutions 300 dots per inch. And with this we have created analytical IDF. I'm gonna show it from here because it's gonna be better. So this is our plot. Okay, good. This is all for this exercise, which is the most important in this precipitation part of the module. Any questions are welcome via email or Moodle. Thanks a lot.